Swayam Prabha. Digital India. Educated India.
So the next subsystem used in laser beam based powder bed additive manufacturing is the powder recoating system. There are several options for powder recoating systems and the popular ones are written here. The first one is utilizing a blade. When a simple blade is utilized, it is nothing but a vertical thin wall of either metal or ceramic or soft blades like of silicone. The mechanism is very simple. As you are seeing a blade here, it collects the right amount of powder in front of it from the powder delivery system that we have already seen, either from the bottom side or from the top side. Then this right amount of powder is spreaded on the substrate or pre-built layer. Typically, such blades are called as doctor blade, and which we have already discussed in SLA also. Ceramic blades are more popular to do not allow any deviation in the part while it is built. So, for example, if there is a ceramic blade which will not tolerate any deformation in the part while recoating and there may be a collision. As this collision happened, the entire machine switched off. So, if there is any small deflection in the part while it got deposited due to the residual stresses or some other means, definitely the recoater will hit it and stop. The benefit of using the ceramic blades are because they are very accurate, and as they do not allow any deformation in themselves, they can deposit the layer very uniformly throughout the bed. So, all the accurate laser beam based powder additive manufacturing system typically utilizes the ceramic blades. In some cases, the ceramic blades can be replaced by the metals also. However, when we use the metal, there are always issues related to the contamination, and also the metal blades life may not be very high. The third option, which is the silicone blades, they are typically used when the accuracy is not very important, but the system becomes a little bit robust in that case, and it allows the blade to get deformed if there is slight deviation. However, such type of systems may lead to accumulation of the error in the part, and hence the error may increase very largely, and at the end, if the diffraction is too high, definitely the silicone blade will deform, but the deflection will hit the top part of the or the solid portion of the recoater blade, and that may damage our machine. Another option is by utilizing the rollers. There are two possibilities of using rollers. So, usually these rollers used to have 2 degrees of freedom. One corresponding to the rotation about its axis, the roller itself rotates and it moves forward as well. These 2 degrees of freedom in the roller while spreading a layer on the powder bed gives us different kinds of freedom. For example, you are having a roller which is rolling in the forward direction, means it is rolling in the direction in which you are moving as well. These type of rollers are called as forward rotating rollers. The benefit of having a forward rotating roller is that the material which is available in front of it, it will spread it by the translation motion of course, but due to the forward rotation of the roller, it will compact the powder also available underneath the roller. However, in that case, we have to be very careful about the flowability of the powder. If the flowability is very bad, it will be very difficult to spread a very uniform layer by this process. However, the another method is the counter rotating rollers. These counter rotating rollers rolls in the opposite direction as in the travel direction. So if they are moving forward, they keeps on rotating opposite to it. Due to this opposite motion, the material available in front of the rollers is also pushed up and gives us a freedom to spread the layer appropriately onto the powder bed. So an example of the forward rotating roller and the counter rotating rollers are shown here. As you can see, this is the material available. This is the powder material available, which is collected from the powder delivery system from either bottom feeding or the top feeding, and then it is spreading it on the pre-build or the previous layer. So this amount of powder is getting compacted while spreading on the bed due to the forward rotation of the roller. While in the case of counter rotation, when the roller is rotating like this, it will pull up some material from here and make it always available in front of the roller. Hence the flowability of the spreading is better in the counter rotating rollers, but we will not get the advantage of compaction here. The compaction will be definitely missing in this case, while compaction will be high in this case. We know that if the packing density of the spreaded layer is better, of course the parts produced in the end by the process will have definitely better density. The third possible option is the slot feeder. The slot feeder is the most easiest way of spreading the layer. In this case, there is a right amount of powder available always in the hopper on the top, and when this powder bed goes down by the desired layer thickness, it leaves a cavity here. When this slotted feeder moves over this, of course the powder will flow and it will get spreaded onto the cavity here. However, here one can notice that the speed of spreading the layer is going to be very slow, because you have a huge amount of powder on the top, as well as there will be issues related to not compacting the layer as there is no such mechanism available. The fourth popular method for powder recording system is the electrostatic system. This is commonly used for the micro laser beam based powder bed additive manufacturing. So these are the two typical examples for the same. The fundamental is the powder particles usually provided the negative charge by high voltage generator. These negatively charged particles are then available in an electrostatic spray gun. Also, the substrate is given either the positive voltage or it is attached with the ground. Now, as these are the negatively charged particles, they will attract towards the substrate. As a result, they uniformly coat on the substrate. This is a very precise method of spreading the powder particles onto the substrate. But of course, it is more popular for the metal particles, while if you are dealing with the polymers or ceramics, this method is not effective. In line with the similar idea, in one literature, it has been found that the similar way of spreading the layer on top of the substrate is achieved, but in bit innovative way. So there is a rotating system here, on which on top of it there is a substrate which is connected with the positive terminal, and the powders are available with the negative terminal. When the substrate rotates and brings down, it used to have the positive terminal attached with it, and the powders are attached with the negative terminal. Hence the powder particles will get attracted towards the substrate. Then after collecting the right amount of powder from this reservoir, the substrate rotates and comes to the next position. The next position is corresponding to the scanning by the laser beam. So the process repeats itself. It does the scanning of the desired layer in the desired region, and then again the system rotates and goes back and picks the powder. So it picks the powder, scan the layer by laser, and then the process repeats itself. There are few hybrid systems also found in some literature, where a combination of the available methods which I have just explained are appropriately used. Like if you are seeing here, in this method there is a roller which is rotating in the counter rotating direction, meaning to say if you are traveling in this direction, the roller will rotate like this. We know that this type of rotation of roller will increase the flowability of the powder, and it will be very easy to spread the layer uniformly in such case. However, we were missing the compaction part here, because the forward rotation of the roller can only give the compaction. But let us now, after spreading the entire layer, bring this roller back. Now the travel direction has changed, and as the travel direction has changed, this rotation, the same rotation of the roller which was earlier counter rotation, now has become the forward rotation. As a result, while bringing this roller back to the home position, while coming back, due to its forward rotation, the powder particles will get compacted here into the very dense spread layer. So the powder compaction is happening along with the powder dispenser by utilizing the counter rotating and forward rotating rollers appropriately. So it's a hybrid system. Also, one can use the blade and roller together. So what is the need of using at all a blade? It has been found that to spread a very large amount of powder, you will require a very large wheel, because otherwise you will not have sufficient amount of powder particles available in front of the roller. So this increase in size of the roller makes it very difficult to rotate it and control it while spreading the powder over the substrate. Therefore, a combination may help. In the first stage, a doctor blade, which is nothing but a vertical wall which can have a large reservoir of the powder particles in front of it, while spreads the layer onto the powder bed, and then a counter rotating roller moves over it and also which vibrates in vertical direction. That gives the compaction to the deposited or the spreaded layer. So as you can see in this diagram, a doctor blade is first used to spread the layer of powder. As here lot of powder is available in front of the blade, it will be very easy to spread large amount of powder on a very large bed as well. Then a vibrating counter rotating roller is now available, which is going to make sure that that deposited layer of the powder got compacted as well to increase the pack density. So these are the popular powder recoating systems for the laser beam based powder bed additive manufacturing. So while spreading a new layer over the bed, we have to be very careful while keeping the or placing the part onto the bed. So for example, we should be always careful that if this is the line corresponding to the recoater's front end or the front edge of the recoater, then we should have least edges of the part, those are just parallel to it. Because if at any slice there will be many lines parallel to the recoater which is spreading, the drag will be more onto the part, and it may be possible that the recoater may dislocate your part, and in that case you may not be able to get a good part after deposition. So for example, we are building a cuboid and at a particular slice we are getting this rectangular cross section. Now the idea is we should not keep it like this as you are seeing here in this diagram. Instead, we should rotate the part in such a way that these parallel lines can be avoided. Now the tilted position is like you are seeing here in the green color, and this line is no longer parallel to the front edge of the recoater. So this is a correct way of placing the part onto the bed. Also, we should be careful while keeping multiple parts onto the bed, like as you see here in this diagram. Here there are part 1, 2, 3 and 4, and they all are kept one side by side. Here what may happen, for example, there are some issues related to with this part, maybe it got deflected, assume that, hence it will stop some material here, right, while the recoater will spread the layer, it will stop that material here. As a result, less material or no material will get deposited here. But as there is a part here on the back side of it as well, it will be possible that the error may propagate even into the fourth part. So any defect which unknowingly coming into part 3 got spreaded now to part 4 as well. Therefore, we should not keep the parts like this as you are seeing in the image, meaning to say not side by side, so that we can avoid the error produced by one part to the another part. The correct way, if for example making this kind of object, will be to spread the parts onto the bed appropriately in such a way that there will not be two subsequent parts while spreading the layer. And also one can notice the edges of the part are not parallel to the front edge of the recoater, and this already been discussed in the previous case. Now let us discuss about the build atmosphere in a laser beam based powder bed additive manufacturing system. There are three possibilities. Either the machine could be having an inert atmosphere, or it could be in an open environment, or the third possibility could be that the machine is in vacuum also nowadays. So the first option, which is the inert environment, is more popular, and particularly it is for the metals. Why it is important? It is important for first to increase the efficiency of the process, and second to create the better parts without any oxidation. So oxidation is the another important criteria here. So let us talk about the oxidation first. As these spherical particles are very tiny in size, hence the surface area is quite high. Therefore, immediately when they come into the contact of the open environment, it is a possibility that the powder got oxide, and that too, if the powder particles are subjected to preheating, then the chances of getting them oxide will be too high. Therefore, to avoid that, the entire environment got usually purged by an inert environment such as nitrogen or argon. In some machines, CO2 is also used to create the inert environment. Also, after creating or completing the part, it is also important that we recollect the unused part appropriately and reuse it. But if the whole thing is happening into the open environment, then it will be very difficult to collect the part in the appropriate metallurgical state, because it may happen that the adjacent part, which is underneath the part or maybe adjacent to the part, got very high temperature, and if it is in open environment, definitely its metallurgical properties will change. Therefore, it is a wise advice to use the inert environment into the machine so that you can avoid these powder particles to get oxidized and later on can be reused. As a result, the efficiency of the process can be increased. Also, a laminar flow of the inert gas over the powder bed will also push away all the fumes generated or the powder particles, those got spatter out of the molten pool, and try to go here and there, and there is a smooth laminar flow of the inert gas will take away all these fumes and protect our machine's top area, which is correspondingly to the optics appropriately. But nowadays it has been found that vacuum is also getting popular for the laser beam based powder bed additive manufacturing. However, we know that for a typical laser to travel, vacuum is not really required. It is required for electron beam. But if vacuum is available with a substantially efficient price, then definitely it can be utilized. Here in this case, the vacuum of very high level is not usually achieved, but a vacuum is sufficiently enough to sufficiently remove the appropriate air molecules from the powder bed chamber is utilized here. This system is very much applicable for the metals, those are very reactive with the gases, those are available into the air if the temperature of the powder particles are high. Another importance of vacuum is that it minimizes the convection heat transfer into the powder bed chamber. As a result, the temperature of the entire bed may remain at the uniform temperature. As a result, the chances of residual stresses will also reduce as the whole bed will be at a particular preheated temperature. Such a system, so the commercial machines with vacuum may be available soon, but these are still under development. The third one is the open environment. In the open environment, no inert gas atmosphere is used and the process happens in the open environment only. It is quite popular when we used to process the polymers. Next and the last one is the build platform. The build platform usually should be of the same composition which is of the material. Also, it should be noted that the temperature of the build plate usually increases in order to make proper bonding between the layer deposited and the substrate. We should also avoid the substrate those usually gives us a brittle interface while depositing a powder layer onto it, because this brittle interface may lead to crack after some time and they will delaminate basically the part from the substrate itself. For the preheating, the temperature of the substrate may even go up to 1000 degrees centigrade in a few cases, particularly for the brittle materials. Also, the area of the substrate should be sufficient enough to accommodate the part on it. In an average laser beam based powder bed additive manufacturing system, the size of the substrate is typically 250 by 250. Now, if we use multiple lasers, the bed size can be increased and it may even go up to 800 by 800 mm. After completing the part onto the build platform, usually it is removed by the wire cut EDM, and the build platform again is grounded and then again reused to build the part on it. So, the substrate which we usually using should be carefully monitored whether it is capable to be reused or now the metallurgical properties has changed a lot, and if they may create issue, the build plate should be changed. So, with this we completed all the subsystems usually available in a laser beam based powder bed additive manufacturing system. So, let them put together and it will look something like this. So, if we summarize again, to join the powder particles together, the different joining mechanisms are available. It can be done by sintering, liquid phase sintering, or complete melting of the powder particles. The powder material also could be coated powders, mixed powder, pre-alloyed powder, polymer powder, or metal powder. The scanning system also could be the galvanometer, it could be the flying optics, or it could be the mask as well. The powder delivery system also we have seen, it could be either the top feeding or it could be from the bottom, and that is called as bottom feeding. Powder recoating systems could be a blade, a roller, a slot feeder, or an electrostatic mechanism. The build atmosphere could be an inert atmosphere, or it could be vacuum, or it can be an open environment. So, let us now start discussion on different type of combinations for different subsystems available in laser beam based powder bed additive manufacturing. So, let us consider first, if the joining mechanism is sintering, it uses polymer as the powder material. It uses galvanometer to scan the laser beam onto the powder bed. It feeds the powder from the bottom, and the rollers are usually available to spread the layer onto the powder bed. Also, it is happening into the open environment. So, this used to be the first system by EOS where the polymer was used and this type of arrangement were preferred. I must be missing some of the previous systems, but this was the most popular one. The another slight modification in the system could be, now as the joining could be the sintering mechanism, powder material will be polymer, the galvanometer will be used for scanning the powder bed, bottom feeding of the powder, and a blade will be used to spread the layer onto the powder bed, and then an open environment will be used instead of having any inert or vacuum environment. So, this is the typically latest system of the laser beam based polymer powder bed additive manufacturing. As you can notice that in such a system, sintering is used. Therefore, the powder particles are not getting melted completely. Also, the polymers are used as the powder material. Therefore, theoretically, any complexity into the geometry of the part can be processed through this system. There will not be also any requirement of any support mechanism. We have already seen that support mechanism is already available in the form of loose powder for the overhanging features in such a system. Also, as the thermal expansion coefficient will be very less for polymers, they are not also going to deform much. Therefore, they will not need to provide support also to restrict the motion or to restrict the deflection of the layer deposited in the upward direction also. Hence, the loose powder is sufficient enough to provide the support to the build part. One example you can see here, it's an assembly which is completely built by the powder material to be used as polymer in the laser beam based powder bed additive manufacturing system. Here you can see that it is an assembly, and it was not like two parts were built together and then we bring them together. The whole thing was built in a single go. And even though if there are any overhanging features here, no need to provide support because the loose powder itself was the support mechanism here. And as a result, the entire part could be built without any issues. Of course, the loose powder later on has to be removed. It can be removed either by shaking the part like this, or if the powder is getting stuck at some very remote location, a compressed air can be used. The parts produced by this method are quite strong even though they are of polymer. This is because the sintering has happened between the powder particles and they are making a very rigid structure in that case. It is also possible the another type of combination used in the laser beam based powder bed additive manufacturing is when sintering is used for joining the powder particles together, but instead of using a pure polymer, the coated particles are used. Coated particle means the structure particle could be either the ceramic or it could be the metal, while these metal or the ceramic particles will be coated by the polymer around it. These are typically called as the coated particles. Then again, the galvanometer will be used to scan the top layer of the powder bed. Bottom feeding mechanism will be used to deliver the powder. A blade will be used to spread the powder particles, and the process will happen in open environment as we are only going to melt the coating which is nothing but of polymer. Such a system found its application in making the objects of ceramic. So you can make the entire casting mold by using this process, and that too without using any pattern. So if a casting mold has to be prepared which is very complicated in shape, as I already said, no need to make the support structures here. The loose powder itself will act as a support, hence any overhanging feature or any complicated shape can be built by this process if sintering is happening. Therefore, the ceramic particles are joined together with a medium of the polymer. After completion of the sintering onto the powder bed, the green parts are taken out, they kept into the furnace, the binder is burned off, that leaves the cavity behind. In those cavities then another infiltrate material is bring into the contact in the molten form of course, and due to the capillary effect the infiltrate material can reach into these pores to make them quite dense. Once the sand molds are ready, you can pour the molten material into its cavity, which can get solidified after some time, and you break the mold and get the metal part out. The another variant of the system is when sintering is used for joining the powder particles. The powder material is again the coated particles. Flying optics is used to scan the laser beam onto the powder bed. Material is fed from the top side and a slotted feeder is used to spread the layer of the powder. And then the whole thing happen in an open environment, and hence the layers are joined in the open environment without using any vacuum or inert environment. The next variant is when the sintering is used for joining the powder particles. The powder particles are coated with some polymer. The mask is used to scan the whole layer in a single go instead of scanning by flying optics or galvanometer. top feeding or the bottom feeding is used to feed the material, and if top feeding is used, slotted feeders are used, and the whole thing is happening in the open environment. Then after that we'll come to the direct selective laser sintering, where liquid phase sintering is the main mechanism for joining the layer. Usually a mixed powder material is used. Galvanometer is used to scan the laser beam over the powder bed. Bottom feeding is used to deliver the material, and a roller is used to spread the powder particles onto the powder bed. And then an open environment is used in the machine. Another variant could be the liquid phase sintering is used, the pre-alloyed powder particles are used, galvanometer is used to scan the top layer of the powder bed, bottom feeding is used to make the powder available for depositing onto the powder bed, and then rollers or blades are used to spread the layer, and the whole thing is happening in an open environment. The another variant of the system is when the joining is happening by the melting of the powder. The powder material is the metal. Galvanometer is used for scanning the top layer of the powder bed, and bottom feeding is used for feeding the powder material to deposit onto the bed. Then blade is used and inert environment is used. So here the difference is, in the last case we were using the top feeding, here the bottom feeding is used. And this is the bottom feeding, and this particular system what you are seeing right now on this screen is more popular in all the existing machines. If you talk about the machine by EOS, the machine by Renishaw, the machine by DMG, all are used to having the bottom feeding mechanism and available options of the subsystem like I have shown here. Now, like I said, there is an emerging field for the build atmosphere, and that is vacuum. Rest of the things are similar, like melting is used to join the layers together, metal powders are used, galvanometers are used to scan the top layer of the powder bed, bottom feeding is used for the powder delivery system to make the powder available for recoating, and a blade is used for powder recoating. The whole thing is happening now in the vacuum environment. Next is when melting is happening to join the layers together, metal is used as a raw material of the powder. Flying optics instead of galvanometer is used now here in this particular case for moving the laser spot beam onto the powder bed. The powder is delivered by the bottom feeding. The blade is used to recoat the new layer, and an inner environment is used into the machine for the build atmosphere. So one such system by exact metal is shown here in this video. Here the laser beam is coming from the top and it is flying on a XY table. Then the new layer is spreaded, and then again the laser scans the area wherever it's required. Here, like I have said, the laser beam is always falling perpendicularly onto the bed, hence you can have a very large bed also in that case. There is no galvanometer is used to deflect the laser beam onto the powder bed. So this is an example of flying optics used with the laser beam. So these are some parts built by such a machine. Here you can see they are fully dense part of monolithic metal. This is of stainless steel, and you can see that a very complicated structure have been obtained. Here one can notice that also there was no support mechanism used, although there are overhanging features. So it means that first of all it was appropriately oriented onto the powder bed before building it. The orientation also decides the overhanging feature onto the part. If the orientation is appropriate and all the overhanging features are within the limit of manufacturability of the machine, then definitely it is possible, because all of these systems can sustain a certain amount of overhang, but if it is beyond a certain limit, then definitely some support mechanism will be required to pull it back and not allow it to warp up. So as you see here, even though it's a very complicated shape, by appropriately orienting it into the machine, one can realize it even without the support. As the laser beam spot size is also very less in this case, in such system it's around 60 to 70 micron, you can really create very tiny features. And if the overhang of these tiny features are appropriate, like not really very much overhang, then the support may also be required. If the support is not required, then you can create really complicated structure but of very tiny feature as well. So this is an example of the latest structure built in the laser beam based powder bed additive manufacturing system. Here the feature size is very tiny, and this feature size are coming because of the spot of the laser size. Also, while the overhang is not very large, they are at a certain angle but not really tilted a lot. If they are tilted a lot, then definitely some support will be required, and removing that support will be then a very difficult task. Such lattice structure help us in providing the high strength to weight ratio component. Individually, each feature may not be very strong. Even I can break the feature by hand. So here I have break it by hand, a simple feature from this part, but together they are very strong, and even I can stand over it and it is not going to deform. As a result, such parts give us high strength to weight ratio and very much applicable for lightweighting the existing conventional parts nowadays. These are some other examples built by the similar SLM machine, the selective laser melting machine, and also these are also the fully dense part of around density more than 99%. This is another example. So this was about the laser beam based powder bed additive manufacturing system. Thank you very much.